This video is on electron configurations and atomic orbitals. We'll be using this guided notes packet for this video. Okay, so to start off, we are talking about the discovery of something called orbitals, okay, or atomic orbitals. So this was 1926, and there was a scientist by the name of Erwin Schrödinger, and he was a mathematician, and he used high-level calculus and looked at some very intense equations, okay, and he used these equations based in calculus to predict the probability of locating an electron in an atom. So if you recall very, general chemistry, our atom has a nucleus, and in the nucleus are the protons and the neutrons, and out here in the, cloud, so to speak, which is what you're taught, are where your electrons live. But for a long time, there was a question of where exactly the electrons live. You know, when you're super young in 8th grade, you're taught that they live on, these energy levels, or they orbit the nucleus, okay, and that's all false. So Schrödinger set out to answer the question of where do these electrons live, and he did it by solving these very advanced equations based in calculus. And so the solutions to these equations, calculus-based equations, gave three-dimensional shapes. Okay, so I always talk, when I teach this in Chem 1, I always talk, about how, in math class, you're very used to taking equations and graphing them. And, we're used to seeing equations like straight lines, okay, is the first type of, graphical interpretation of an equation you do. And when you get more advanced, you do parabolas, right? And then you get more advanced than that, and you do, sine and cosine curves and things of that nature. But we're talking, advanced calculus, that when he took these equations, or the solutions to these equations, and graphed them, he got three-dimensional shapes. And those three-dimensional shapes are called orbitals. Okay, atomic orbitals to be exact, because later on in this course, we actually talk about molecular orbitals. So these are atomic orbitals, which are or orbitals on atoms. And these orbitals are defined as an area where the probability of finding an electron is high. Okay, and that's what an atomic orbital is. It's a three-dimensional region of space where the probability of finding an electron is high. Orbitals have some specific characteristics in that they have a specific shape, which we're going to talk about in just a minute. There are actually 4 types of orbitals. They have different shapes. So they have a specific shape, and they have a specific energy, a value that goes with that orbital. Okay, so these three-dimensional regions of space are called orbitals. They hold electrons, and they have specific shapes and specific energy values. All right. All right, so your next heading is representations of the atomic orbitals. Now, when we get back into class, I will show you some three-dimensional pictures or even models of atomic orbitals, but for now, my dry erase board and my marker will have to do. All right, so we're going to build a little chart in this section, a four-column chart, orbital shape, something called orientations, and max number of electrons. Oops. Okay, maximum number of electrons over there. Now, if you, we did this in Chem 1, if you remember from your Chem 1 discussion on electrons, we went over the types of orbitals, their shapes, how many orientations they have, and how many electrons can live in each orbital. There are 4 orbitals, and they're represented or designated, I guess, by letters. There's the S, the P, the D, and the F. Okay, the S is shaped like a sphere. So I know that's a circle, but it's supposed to be a sphere. So think, basketball. And the deal with the orientations is how many ways can we take a sphere, okay, a perfect sphere, and move it in space so that it looks different to you. And because it's a perfectly symmetric sphere, the answer is there's only one, okay? It's only one orientation. And we'll see how that changes in a minute. And the rule with orbitals, which we'll get more in depth here in a minute, is that any orbital can hold a maximum number of 2 electrons. So the orbital can hold 1 electron, it can actually have 0 electrons, and maximum it can hold 2 electrons, but no more than 2, as that is the maximum number of electrons. So after the s orbital, we have the p, and the p is shaped, it's shaped like a dumbbell. Okay, we'll kind of draw it like this. Shaped like a dumbbell is the slang name for it. And there are 3 orientations of the p. If you think about it, they're aligned along the x, the y, and the z axis. So the p orbital aligned along the x would look kind of like this, right? Think x as horizontal. The p orbital aligned along the y would look like the one I drew here, okay, the vertical one. And then there's a z axis, right, which is your third axis that's, coming out of the board to you. And so that one would be hard to draw, but from the front would kind of look like an s orbital, and then that back lobe is behind it. Okay, think about me holding my marker, right? This is aligned along the x, this is aligned along the y, and this is aligned along the z-axis, okay? And conveniently, this is what we call them. We call this the px, the py, and the pz. So there are 3 orientations here, and each one of those orbitals, okay, orbital, 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 each one can hold 2 electrons. So 2, 2, and 2 max, making my total number of electrons 6. The next orbital is the d. As we get higher in these orbitals, they get more and more, I don't know what word I want to use, but they get crazier, for lack of a better word, in their shapes. And so the d looks kind of like we call it a clover leaf. Okay, it looks like a 4-leaf clover, so to speak. All right, like that. And there are well, I'm jumping the gun here. I apologize. There's actually a second shape to the D. It's getting kind of specific, but it looks like a P like this, and it has a kind of a donut shape around the middle. Again, I'll show you these in class in a computer-generated image of them. So in terms of orientation, this is a little harder than just lying along the PX, PY, PZ. So there are 4 orientations of the clover leaf, okay, how they're, facing in space. And again, I'll attempt to show you that in class. And there's one of these P with a donut, for lack of a better word, giving you a total of 5 orientations. And again, each one of those orientations can hold 2, so 5 times 2, max number of electrons would be 10. And the fourth and final type of orbital are the f orbitals. They are kind of like the d orbitals doubled, so it's like 2 clover leaves stacked on top of each other. And there's even this p orbital with, instead of 1 donut, there are 2 donuts. And these orientations, I'm not even going to attempt to draw them. There are 7 of them total. And again, each holding 2 electrons gives you a maximum number of 14 electrons. Okay, so these numbers over here, this 2, 6, 10, and 14 is extremely important. And there's a huge connection to the periodic table, and I'm sure you may remember that from Chem 1. All right, so underneath this chart, there's a periodic table. I'm going to go ahead and draw you one and give you a bit of a discussion. So we'll remember those 4 or number of electrons. S holds 2, P holds 6, D holds 10, and F holds 14. Those are super important to us. Okay, so real quick, here's my sketch of a periodic table. Okay, and then I have my 2 rows underneath. Okay, so huge takeaway point is that your periods in a periodic table, which are your rows, right, your horizontal, and they are numbered 1 through 7, 1, 2, 3, 4, 5, 6, and 7. And this technically is period 6 and period 7. Those are also your energy levels. Okay, huge takeaway. So periods are equal to the energy levels. And if you can remember back, to 8th grade chem or 7th grade, science, 8th grade science, when the first time you learn about this, you have the nucleus, and then, you know, on this first energy level, you had electrons. On this second energy level, you had electrons, almost like an orbit, right? So that's what we're talking about. We're talking about energy levels. Okay, so meaning we have the first energy level, we have the second energy level, we have the third energy level. And my picture's a little off here, guys. Let me fix this. Okay, there we go. So we have the third energy level, the fourth energy level, the fifth, the sixth, and the seventh. Okay, and so on and so forth. So the big kicker is, how do these numbers play into the periodic table? And when you're in Chem 1, I ask you to kind of hunt for it. I ask you to find the connection for me. And we even color code our periodic table this way. And the kicker is that these first two columns, since it's 1, 2, 1, 2, 1, 2 all the way across, including helium, this is representing the S. So if you want on your little periodic table, you know, right here, you can color code it. I did. I color coded my electrons and then color coded my table to match. So there's your 2. Okay, it's referred to as the S block. Okay, so this is the S orbital. And so then we hunt for the 6, and the 6 is over here. Okay, if you count across, 1, 2, 3, 4, 5, 6, there's 6. This is referred to as the P block, matches with the P. The inside here, the mostly transition metal section, if you count across, there are 10. This is the D orbital, it's referred to as the D block. And then if you count across the bottom, there are 14. Okay, and this is the F, so referred to as the F block. And so that's the huge connection. So the takeaway is that you can follow the periodic table to determine the filling of these orbitals, and it's so convenient and so nice. I'll show you on a real periodic table. Hope are we in focus? Yeah. Okay, so meaning if this is the first energy level right here with hydrogen and helium, that's also the S. So this is the 1s orbital. Notice it can hold 2 electrons, 1, 2, right? Perfect. Then we jump down here, we're in energy level number 2. So this is the second energy level, okay? The 2s holds 2 electrons, and then the 2p holds 6 electrons. So far we've got the 1s, the 2s, the 2p. If we keep going in that fashion, this is the 3s holds 2 electrons. The 3p holds 6 electrons. Keep going. The 4s holds 2 electrons. Here we run into an issue where we think this would be the 4d, but in fact it's not. There's a kind of an oddity that occurs, and the D's are almost like they are taken and bumped up 1 energy level. So this is actually the 4s, but it's the 3d. And then it goes back here to the 4p, 5s, 4d, 5p, so on and so forth, okay, until we get to the end. When you get down here to the F's, which remember, they come right into here, okay? So F's are a little strange. We don't do much with them, but they might pop up once or twice. The F orbitals, so think about this. This is the 6s, right? But the 5d, and then this is actually the 4f. Okay, so they even bump up 1 more. So you might want to make note of that on your table. But if you notice, your kind of cheat sheet notes have that written on there. Another model of the orbital filling right there, if you want to take a look at that, just as a graphical representation with your energy, like on your y-axis, okay, showing you low energy to high energy. Obviously, the 1s has less energy than the 2s, because it's in the first energy level. Okay, so that was quick, but a nice intro. We are going to do the first 2 sections on this next page, and then that will be the end of this video. All right, so we have 3 rules that govern the filling of orbitals. Okay, and those 3 rules are the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Okay, the Aufbau principle is the easiest one, and it says electrons fill lowest energy levels first. Okay, so that means that if an electron can go in the first energy level, it's going to. It's not going to go into the 6th energy level if there's room in the first energy level. Okay, so when we fill electrons, we always start at the lowest energy level. Meaning, if you're using like your chart like this, if we're filling electrons, we're always going to start here with the 1s, fill it, and then go to the 2s, fill it, fill the 2p, so on and so forth. That's the first rule. Second rule is called the Pauli exclusion principle, and it says an orbital can hold 2 electrons, max, okay, maximum of 2 electrons, only if they have opposite spins. So we don't really talk a whole lot about the spinning of the electron, but if you think about it, these electrons are moving, some are spinning clockwise, some are spinning counterclockwise. Pauli exclusion says 2 electrons can live in one orbital as long as they're spinning opposite ways. So you'd have to have a counterclockwise and a clockwise. That's too hard for us to draw, so we denote it with arrows, one going up and one going down. So for example, if we're going to draw a 1s orbital, okay, that's holding 2 electrons, then I have to draw one arrow going up and one arrow going down. And that's Pauli exclusion. It says an up and a down can live there, but not 2 ups and not 2 downs. So Pauli says opposite spins. And Hund's rule has a vocab word. So before I do the vocab word, I'm going to define this. Before I do the rule, I'm going to do the vocab word. If you want, you can define your word up here in this space. It's not going to take very much room. The word is degenerate. Okay, the word is degenerate, and all it is orbitals of equal energy. So if you go back to your chart here, okay, where it was showing you based on the energy, if you notice, the 1s, there is no other orbital with this energy. The 2s, there's no other orbital with this energy. But if you look at the 2p, sorry, there's my dogs. If you look at the 2p, there's the px, the py, and the pz that all have exactly the same energy. So a perfect example of degenerate orbitals are the 2p, the 2px, the 2py, and the 2pz. Okay, so all of these orbitals have exactly the same energy. So Hund's rule says that electrons will fill degenerate orbitals as single electrons before doubling up. Okay, electrons fill as single electrons before doubling up. So what that means is if I have 3 electrons to place in the 2p orbitals, that I'm going to put 1 electron in each orbital because this rule says they're going to fill as single electrons before they double. Meaning that if I had 3 electrons to place, I would not do this. Okay, because I haven't filled them all as single electrons. And when I teach this in Chem 1, if you recall, I talk about siblings and bedrooms, right? If you have 3 siblings in your house and you have 3 bedrooms, the chances are they're all going to want their own room. They're not going to double up and leave a bedroom empty. And the same is true for electrons. Think about it. Electrons are negative, right? And negatives don't like other negatives. And so we're already housing 2 electrons in the same, bedroom, so to speak. And so there are some repulsion situations going on. Okay, so those are your 3 rules. A quick rundown of electron configurations 3 ways, and we are done. We will save the anomalous electron configurations for class. So the first one is called electron configuration notation, or just electron configuration. And I'm going to do all these examples with calcium, okay, so we can see the difference. So I'm doing all these examples with calcium. All right, so for electron configuration, I start with my periodic table. I start at the top with hydrogen, and I start filling my orbitals. And I'm going to stop when I get to calcium. So the first orbital is the 1s. And it holds 2 electrons, 1, 2, and it is full. And it's written like this, 1s with a subscript of, it's not a subscript, I apologize, it's a superscript, 1s2. Following 1s2, I fill the 2s next, so 2s, 2. Following 2s comes the 2p, and it is full with 6 electrons. If you're unsure, you can count, 1, 2, 3, 4, 5, 6. Okay, following 2p comes the 3s, 2, and then the 3p, 6. And then following 3p6, which would leave us here with argon, we go here to 4s, and 1, 2 brings us to calcium. And so that is the electron configuration for calcium. Notice the highest energy level is level 4. 2 electrons, those are the 2 valence electrons. These are all the core electrons. Okay. Second way to do this is orbital notation. This is no one's favorite way, only because it's involved. Okay, orbital notation is the arrows. So if I'm going to draw calcium, I'm going to denote these orbitals with lines and arrows as electrons. So I draw the 1s, it's full with 2 arrows. I go 1 up, 1 down. I shortcut my the top of my arrow so that I can do it in 1 pencil stroke. You're welcome to do the same. Following the 1s comes a 2s. I can use this as my guide with an up and a down. The 2p, there are 3. Remember, it's degenerate. 2px, 2py, and 2pz. So technically it feels like this. Up, 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 down, down, down. Okay, 2p is full to the 3s, just one of them, up, down. The 3p is also degenerate with 3px, 3py, and 3pz. Technically it fills up, 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 down, 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 and then a 4s, which is full with an up and a down. So that is calcium's orbital notation. And then the only other one we have is the noble gas. It's also referred to as the condensed electron configuration. Oh, I should have left that up there. Hold on. Well, I'll just rewrite it. Okay, so to do a noble gas, we look at our periodic table, we find calcium, and we backtrack to the noble gas who comes before calcium, not after. So before is argon. We put argon in brackets, and we continue the electron configuration after argon until we get to calcium. So we pick up right here, 4s, 1, 2. And that is the noble gas configuration for calcium. I'll show you why it works, and then we'll be done. So if you recall calcium's configuration that we just had up here, oops, yeah, okay, that's calcium's configuration. Well, argon's configuration is this. Okay, so what essentially we're saying in a noble gas configuration is, look, argon has calcium's configuration, has its exact same configuration, except that then we attach a 4s2, and that's why noble gas configuration works. So those are the 3 ways to write electron configurations, and we will go over the anomalous electron configurations in class.